In this lecture, we shall continue our discussion on the quantum theory of hydrogen-like atoms. In the last lecture, we have found out the solution of the Schrödinger equation in spherical polar coordinate geometry, and the solutions were solutions were this is the radial solution, and it was the theta dependent part, and the phi dependent part was this. Where the functions L n plus L, and this is twice L plus 1. This is associated Leguere polynomial, and this one is associated Legendre polynomial. And where rho is twice z divided by n, a naught, and here r, and this a naught is a constant, and which is given by this. The values of small n restrict the values of L, and the values of L restrict the values of M. As a result of these restrictions, these three quantum numbers N, L, and M, these are the quantum numbers. This is known as principal quantum number. This is angular momentum quantum number. And this is magnetic quantum number. And these three quantum numbers, these quantum numbers take the values the principal quantum number is 1, 2, 3, like this, positive integers, and L is 0, 1, 2, like this, and M is minus L plus 1, dot, minus 2, minus 1, 0, 1, 2, dot, 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 L, and then L plus up to plus L, then L. So the relation between N and L is N is greater than or equal to L plus 1, and corresponding to a single value of L, there will be twice L plus 1 values of M for a single value of L. There will be twice L plus 1 values of M, the magnetic quantum number, indicating by subscripts the quantum numbers upon which each function depends. We can rewrite the total solution of the Schrödinger equation for the hydrogen-like atom can be then written as and this one can be written as combining the theta and phi dependent factors together, and these two, the product of these two is written as YLM, and function of theta and phi, where RNL of R is the radial wave function, and YLM of theta phi is the product of two angular wave functions and represent the spherical harmonics. Now we discuss about atomic orbitals. The wave function for an electron corresponding to certain fixed values of n, l and m is called an atomic orbital. The wave function for an electron corresponding to certain fixed values of n, l and m is called an atomic orbital. It is convenient to describe atomic orbitals in a shorthand notation. Generally, the orbitals with L equal to 0, 1, 2, these are referred to as, for L equal to 0, this is a S orbital. For L equal to 1, I will call them P orbital. And L equal to 2, D orbitals. And so on. Moreover, the numerical value of small n is placed before the letter specifying the L values. For example, an orbital with say n equal to 1 and L equal to 0 is called a 1s orbital. An orbital with n equal to 2 and L equal to 1, it is called a 2p orbital, etc. Now for each value of small n, the angular momentum quantum number L can have values for each value of small n. The angular momentum quantum number L can have 0, 1, 2 up to n minus 1 values, and for each value of L, the magnetic quantum number M can have 0, plus minus 1, plus minus 2 up to plus minus L values, resulting in L plus 1 values, or 2L plus 1 different orbitals. Hence, the total number of orbitals for each value of n, for each value of the principal quantum number n, is given by, so we sum up this twice L plus 1 from n equal to 0 to n equal to L equal to 0 to n minus 1, and this gives you 1 plus 3 plus 5 plus and up to twice n minus 1, and which is equal to n square. The solution of the radial equation gives the energy of the atomic orbitals will be given by this. Which can be written as minus z square e square and divided by 8 pi epsilon naught a naught n square, where a naught has been has been defined earlier. Now we discuss about the radial distribution function. Um, the probability of finding the electron in the region in terms of the radial distance from r to r plus dr, if we do not consider the angular part, if the position of the electron does not depend on the angular parts theta and phi, then this probability can be expression for this probability can be found out easily. The probability dp of finding the electron between the radial distance r and r plus dr, theta and theta plus d theta, and phi and phi plus d phi is dp equal to, so we take the modulus square of the total wave function, and which is r of r modulus square theta of theta modulus square and phi of phi modulus square, and the volume element, where dv is the volume element, because the modulus of the wave function square is the probability density. So if we multiply it by the volume element, then we get the probability in this volume dv of finding the electron, and this volume element in spherical polar geometry is r squared sine theta dr d theta d phi. This is standard volume element in spherical polar coordinate geometry. To find the probability, only between r and r plus dr, the angular wave function should be integrated over the full range of theta and phi. Therefore, P probability from R to R plus dr, we integrate over theta and phi, and we put the values of the probability dp here, and this was into volume element r square sine theta dr d theta d phi. So if we integrate over this theta and phi, then we have this sine theta d theta, and we have 0 to phi and modulus of phi square, and this is d phi. If we substitute this, then these integrals will give you unity, and we will be left with, and I'm sorry, there will be a dr here, and this is r of r modulus square r square and dr. This equation holds for both s and non-s orbitals. When the angular variation is taken to be fixed, the function, if we put the subscripts, the quantum numbers, then actually we have the probability here r2r plus dr, and this one we can write down r and l of r and r square dr. And this portion is known as the radial distribution function. This is the end of this lecture. It should be mentioned here that we have not discussed the details about the angular parts of the wave function. The discussion is lengthy, and we shall not consider this in this lecture.